Hello, dear friends. I am Samayat Fanta, research scholar from Indian Institute of Technology, Kanpur, and I come from Ethiopia, Defense University College of Engineering. This is one day online workshop, which is prepared based on the questions raised by many fellow researchers and the students of IIT Kanpur as well as other institutes. So the workshop is prepared by collaboration of IIT Kanpur Aerospace Engineering Department, particularly Aerospace Structural Lab. So my lab mate Sanjay Kumar have truly explained the most important preliminary concept of FEM and the interaction of computer for modeling FEM problems in the morning session. Therefore, I will extend my presentation from the point where Mr. Sanjay stopped. So my presentation contains, let me share the slides. So it is one day online workshop on the structure analysis using FEM tool, Abacus CAE. So the objective of this presentation is to understand FEM modeling approach for different loading scenarios, to develop a stepwise impact model of a laminated sheet or laminated structure by blunt projectiles using Abacus CAE, to explain the finite element modeling procedures of damage modeling of fiber reinforced polymer composite laminates in Abacus, to generate Python scripts while running the Abacus file, or to implement the script to Abacus model, to implement a Fortran developed user material subrouting code like UMAT or ViewMath in Abacus standard or in Abacus explicit. So when we start our discussion, it is better to understand a basic idea of what finite element mean. So the finite element is a numerical technique used to perform finite element analysis of any given physical phenomena. It is necessary to use mathematics to comprehensively understand and to quantify any physical phenomena, such as structures or fluid behavior, or thermal transfer or heat transfer, wave propagation, and growth of biological cells, and so on. Most of the processes are described using partial differential equations, like, for example, for the dynamic problem case, we have an equation of dynamic equation of this type, that mass times acceleration plus dashpot times the velocity plus the stiffness times displacement, which is equal to Fx, or externally excited time-dependent force. For a computer to solve these partial differential equations, numerical techniques have been developed over the last few decades, and one of the most prominent today is the finite element method. Why is finite element method needed? It is highly required to solve the problems, which is the type of explicit or implicit finite element modeling. Also, explicit versus implicit finite element. modeling FEM is used to simulate naturally or artificially occurring phenomena. This numerical technique is the foundation of simulation softwares. In order for generating, in order for engineers, including aerospace engineers, civil engineers, and as well mechanical engineers to assess their design for failure and damage in various loading conditions before going to prototype implementing stage. So we have time-dependent versus time-independent analysis. So analysis can be time-dependent or time-independent. Some of the analysis are time-dependent, which are very mm, dynamic in nature, and some are very static nature. Okay. For all nonlinear and dynamic analysis, incremental loads are needed. This means we need to break down the physics or time relation to solve mathematical problem. To do so, we form two groups, either time-dependent or time-independent problems. To solve such problem, we commonly use either explicit or implicit methods. We refer to the problems as time-dependent when the effect of accelerations are pronounced and cannot be neglected. For example, a drop test, the highest force occurs with the first few milliseconds as item decelerates to stop. In this case, the effect of such deceleration must be accounted for. In contrast to when the load are slowly applied into the structure surface, then the loading can be considered quasi-static or time independent. This is because the loading time is slow enough that the acceleration effects are negligible. Okay. Sorry. Okay. All implicit and explicit problems are expressed using mathematical partial differential equations, while the computer cannot handedly solve PDEs. So they are equipped with to solve matrix equations. These matrix equations can be linear or nonlinear in nature. So in most structural problems, the nonlinear equations fall into three categories. That is material nonlinearity, geometric nonlinearity, and boundary nonlinearity. So material linearity is characterized by the deformation and the strain are very large. For example, polymeric materials. Geometric nonlinearities where strains are small but rotations are large, such, for example, thin structures. And boundary nonlinearity comes due to nonlinearity of the boundary conditions, that kind of contact problems. Implicit FEM analysis. So one method of solving for the unknowns of X is through the matrix inversion. For the nonlinear problem, the solution is obtained in the number of steps, and solution for the current step is based on the solution from the previous step. So for large models, inverting the matrix is highly expensive, especially the stiffness matrix. and which and will require advanced iteration solvers or standard direct solver. This is also known as the backward Euler integration scheme. And the solutions are unconditionally stable in the case of implicit FM analysis and facilitate large time steps. Despite that disadvantage, the implicit method can be extremely time-consuming when solving dynamic and nonlinear problems. The implicit method should be used when the events are much slower and the effect of strain rates are minimal. So this is the scheme of implicit dynamic method, how the software solves. So it is characteristic question, or it is partial differential equation is mu dot plus, that is n plus 1 time increment plus 1 plus alpha ku ku dot, no, this is u, ku tn plus 1 minus alpha ku tn, which is equal to f tn plus 1 plus delta alpha delta t. So this alpha and beta are the Newman beta functions. The Newman beta functions are given. Okay. The first is the governing differential equation, and the second is the equation for u, that is u is equal to tn plus 1, which is equals to u of tn plus delta tu dot tn, delta t u tn, t of u dot of tn plus, okay, okay, plus 1 over delta t square 1 minus 2 beta u dot dot tn plus 2 times beta u dot dot tn plus 1. Again, the velocity is given as u of tn plus 1, u dot of tn plus 1, which is equal to u dot of tn plus u delta t 1 minus gamma u dot dot tn for n time increment plus gamma u dot dot for n plus 1 time increment. So this alpha, beta, and gamma are the called the Newmark functions or Newmark beta functions. Okay, let me write something here. Where is, okay. Newman algorithm. Okay, beta functions. The Newman beta functions are defined as alpha is from minus 1 over 3 to 0. Beta is 1 minus alpha as whole square over 4. Okay, 1 over 4 times 1 minus, okay, gamma is equals to 1 minus 2 alpha, 1 over 2, okay. U of t naught is equals to u naught. These are finally this u of t naught which is equal to u naught, the boundary conditions or the initial conditions. Okay, initial conditions. So the initial condition u of t naught, which is equals to u naught, u dot of t naught is equals to u naught, u dot naught, and u dot t naught is equal to from equation on the governing equation, governing partial differential equation, with alpha is equal to 0 and n is equals to -1. N is equal to -1, alpha 0 means if alpha 0, this part is 0. If alpha is -1, this part is equals to 0. Then we have left f of t, this thing. This all becomes 0. Okay. So this is the implicit dynamic method. And the explicit finite element method modeling analysis. Explicit analysis aims to solve for acceleration. In most cases, the mass is considered as lumped and thus diagonal matrix. So inversion of diagonal mass matrix is straightforward. Diagonal mass matrix is straightforward and includes inversion of terms on the diagonal. So this is the type that the acceleration equation is represented with this. So once accelerations are calculated at the n step, the velocity at n plus half step and the displacement at n plus 1 step are calculated accordingly. So in these calculations, the scheme is not unconditionally stable, like in the case of implicit analysis. And thus, smaller time steps are required. To be more precise, the time step in explicit finite element analysis must be less than the current time step. That is the sound wave, the time taken by sound wave to travel across an element, while implicit analysis have no such limitation. So the explicit method should be used when the strain rates or velocity is higher. Okay. Okay. To explain the dynamic explicit analysis scheme in Abacus FEM, how it is structured, we can start from some schematic dynamic system. This dynamic system consisting of mass, damper, and dashpot, and the stiffness, and which is subjected to some external force F, and with initial displacement, initial velocity, and this u dot at initial are provided. The governing the equation of the system is mu dot plus cu dot plus k u, which is equal to f external. And then in this governing equation, we can apply the Euler, not Euler, but some central difference method, which taking u to t axis and which is starting from n minus 1 to n plus 1 with half division that n minus 1 over 2, n plus 1 over 2, n is there. So taking the equilibrium equation at n, okay, so u dot n minus 1 over 2, which is equal to ui minus ui minus 1 over delta t, u dot n plus 1 over 2, which is equal to ui plus 1 minus ui over delta t. And taking these two equations and applying them to acceleration at the center at n, equilibrium at n, so un is equal to ui plus 1 over 2 minus ui minus 1 over 2 over delta t. So, so from that, what you can get is ui, that acceleration ui dot, which is equal to ui plus 1 minus 2 times ui plus ui minus 1 over delta t square. So, which is substituted to this equation, and m is substituted with this equation. Instead of in governing equation, we substitute ui value here. Again, x ui dot value here, and okay, we have to neglect the damping effect, that very small damping effect, so that neglecting the damping, but considering the damping, we substitute this thing, okay, and ui, that equilibrium at I, which is equal to f external. From this, what you can get is the ui equation. More precisely, we can see this. Okay. This equation gives a clear step on explicit dynamic method. MUI plus KU, which is equal to F, neglecting the damping effect. Then UI at n plus 1 over is equals to UI Tn plus 1 minus U of Tn over delta T. U dot Tn, which is equals to Utn plus 1 over 2 minus Utn minus 1 over 2 over delta T, which is equals to Utn plus 1 minus 2 times Utn plus Utn minus 1 delta T, the whole square. So errors are of the order of second order for the time step delta T approach to 0. So finally, the dynamic equation becomes mu dot tn, which is equals to ftn minus ku tn. And then u dot tn plus 1 over is given as u dot tn. This is the Euler forward, using the Euler forward scheme. And finally applying the initial conditions, u of t naught, which is equal to u naught, u dot t naught minus 1 over 2, which is equal to u dot naught. Applying this, we finally get the solution for all the unknowns. So let's go to the practical problem on damage induced in laminate structure from impact. So we are going to model the foreign object impact on laminate thin structure using abacus. So for the practical purpose, we have to start with some physical program domain and follow stepwise procedures to understand the concepts. Okay, I can leave this. The model contains a rectangular thin plate of ASTM standard size with a thickness of 2 millimeter and is impacted by a rigid tool dropped during maintenance operation with mass of 2 kilogram and diameter of 16. The parts contain the lamina and the impactor. The lamina may be interface and the impactor or projectile are to be modeled using abacus CAE. And the plate is considered to be deformable, deformable and sketched in such a way that 090 symmetric. And it is basic knowledge of, it needs basic knowledge of composite material and abacus CAE. Okay. So the preliminary steps while starting abacus CAE are open abacus CAE from the start session. So let me open abacus. So until it opens. So the next is set the work directory to save all your work or project in particular folder. So we have to create a folder, an empty folder in some particular position or on some particular location. Okay. Folder. Okay, sorry. Save it with name, some impact implicit. It can be your own. For me, I call it impact simulation in the work directory that's already created above. To generate Python script, okay, it is opening. It takes some time. So to generate Python script, we'll go to File, Micromanager, create, give some name with impact, and then continue. And to run simulation in CAE, we can either work with various module. The past. And the simulation in abacus CAE. We can either work with various modules in the drop-down menu or using a workflow tree. Okay, now let's go to abacus file. So this is the appearance of the abacus file. So we start with standard explicit method. I select standard explicit method, and then let me select the work directory. Okay, set. Okay, provide work directory. Move this one. Okay. Okay. Then here let me create impact problem. Okay. Then select that impact problem folder. Okay. Now it is the work directory is in E impact problem. Then okay. Then let's go to run micro. So go to micro manager. Create. Give some name impact. Let it be impact. Impact. Continue. Then leave it as it. Okay, then we can start our work of modeling the plate. So create part. So we have number of modules and workflow trees. We can work either of them. So here many modules are there, that part module, property module, assemble module, step module, interaction module, load module, and so on. And also there is alternatives here in the workflow tree. That part, material, section, assembly, steps, again interactions, okay, constraints, loads, everything is here also. So someone can work with the flowchart, or another one will work with the modules. Okay. So for me, I prepared the modules to work all my modeling. So let me start with. So our part is 150 by 100 by 2 millimeter. Start 090. So I'll create. Okay. Plate 0. Give name plate 0. 3D deformable solid extrusion, and continue. And then I'll create a part with prescribed predefined dimension. So this is the geometric entities are already here. I selected only a rectangular geometric entity, then giving dimension of 150 millimeter, that is E minus 3, and this is 100 E minus 3. Okay, This is the plate, so I want to put it in central position. Here, okay, and let me move it. Yeah, just move. So the center to 0,0 position. Yeah, done. So it is now. Okay, let's extrude it with dimension of 0. Let me give 0.5 millimeter dimension, -3. So this is the plate. So I can copy this plate or create another part for 90 plate 90. So for simplicity, I'll copy this part and give the name. Okay. Copy. And, copy. Okay, rather plate 90. Let me give them 90. So we have two plates of 0.05 millimeter with the name 0 and the 90. And if we want to introduce interface element in between plates or the at the interface to simulate the delamination at the interface, I have to create also an interface line with a very thin minimum of 1/10 of the thickness of the maximum of 1/10 of the thickness of the lamina will be created. So for that, that is, I will discuss it only theoretically, but the main case is we can create it and give dimension. Okay, copy and name it interface. Okay, so now I have to give this extrusion depth of this is very less. That should be 0.005. Let it be 1/10 of the plate thickness. Okay. So a thin sheet of interface is created. That is the third part. So the next is creating the impactor. That the impactor is discrete rigid impactor with shell and revolution. Okay. Okay. So to create the impactor, I will use a circle entity. Okay, circle. Then add dimension to circle. That is 8 millimeter radius. This is the circle with 8 millimeter. Now we can trim unnecessary parts. Actually, before that, let me make it closed form and then trim it. trim the extra parts. So 1/4 of the circle is created now. So let's revolve this to 360 to create. So let this be 360. So this is an impactor. Okay, this is an impactor. So let's name it impactor. Now we created an impactor with the given dimension. So what is the next? The next is you can follow all the steps from the slide. So part module, it contains all geometric entities to sketch and create parts. So we created the required parts, that impactor, the laminate, and the interface parts. And the next is the material module. The second one is the material module. So what can I do in this step? Let me assign reference to the impactor, because each impactor needs some reference point. So reference, let me give this point as the point where the mass of the impactor is concentrated. Okay, that is reference point. And then let's go to the second step, property. The property module helps us to implement materials. Okay, and also it helps us to assign section. Okay, to assign materials, to implement materials, and it has a lot of other importance. Anyways, let's implement materials to different materials, so different parts which are created. For example, for impactor, the only material that we can assign is the weight of impactor here. So for that, we have to give some reference point. Okay, set tools, tools, layer. It is disturbing actually. Okay, tools, set, create, reference. Ref. Then give a reference to this point. Then okay. Then the next is go to spatial inertia, create point mass with inertia, then point mass, continue, show the point where we are going to assign mass, and then the isotropic mass of let it be 2 kg. And the rotary inertia properties remain blank. Okay, then we can see some green color here that indicates that the concentrated mass or lumped mass. Okay, then other materials, material for plate and material for interface are should be created using create material, give material